So remember the steps of outer approximation. I told you that we can solve an MILO stop if infeasible or if nonlinear feasible solve an NLO, add linearizations, and go to 1. Okay. So in practice, if you have a nonlinear objective function, and if you just drop this, then obviously your MILO will be unbounded. Okay, so or it may not give you a lower bound. Okay, if you instead of solving min fx, if you just say I'm going to solve minimum of 0, 0 may not be a lower bound for fx. Okay, so in that case, typically what you start with is by solving the NLO relaxation of the original problem. Okay, solve NLO relaxation of the MINLO. Okay, so in the first one, you don't fix any variables. You just solve the regular NLO problem, and whatever point you get out of this x hat, y hat, you can add linearizations at that point. Okay, and that ensures that you get lower bounds, a lower envelope for or a lower underestimator for fx also. Okay, which you might otherwise miss, if you just look at the slides. Okay. Also the solution that you get here, suppose you get objective value of z hat. Okay, that is an underestimator for your MINLO optimal value. Okay, and if you add the linearizations at x hat, y hat and solve the MILO, what will you get as your objective? Would it be more than z hat, less than z hat, or equal to z hat? More than z hat. Okay, why would it be more than z hat or greater than equal to z hat? So same result. Okay, so you get this KKT point x hat, y hat. You add linearizations at that KKT point. So then this optimality lemma says that once you add those linearization inequalities, all the points must have objective value z hat or higher. Okay, and then if we add even more restrictions of integer variables, the value will be even higher. Okay, so we get a lower bound which is equal to the NLO relaxation or higher if we do this initial step. Okay, so typically solvers will start with this step and then do this loop many times. Okay, and you can stop in between, and if you hit some time limit, you still have a lower bound coming from this step and a possible upper bound coming from this step. Okay. There are many enhancements to this. You don't have to add linearizations only at this step. If you are aggressive and you foresee that lot of steps, lot of iterations are going to happen, then you may as well add these linearizations much earlier by sort of exploring some more points besides these KKT points. So this is the bare bone algorithm. You can enhance it by adding more linearizations, more cuts, more structure dependent rules and such. Okay. As I said, that the biggest advantage of this method is that you can implement it really fast. Okay. So if I told you that let's have a MinLP solver by the end of today, okay, your best bet is to implement this algorithm rather than anything else. Okay, because you don't have to worry about implementing code for branch and bound. You don't have to manage any cutting planes. All that is done by the this solver. You don't have to analyze structure of any nonlinear problems or anything. That is taken care of by this. The only part is that you have to implement some for loop and be able to add these linearizations. Okay, and this is usually done by modeling languages like AMPL. Okay, so one task of these modeling tools like AMPL and GAMS is to translate human readable models into something that solvers understand. But these tools also provide gradients and Hessians at specific points. Okay, so if you want a gradient at a given point, AMPL will compute it for you using techniques of automatic differentiation. Okay, so this is very, very straightforward. Okay, these methods are also called multi-tree methods. And the reason is that in every iteration or in every step, we are solving a mixed integer linear optimization problem, which is a tree-based, tree search-based method. So in every step, you are exploring some branch and cut tree, and then forgetting entirely about it, adding some more inequalities, solving it again and again and again. Okay, so that has some limitations, but it also has certain advantages in the sense that if you initially have a poor branch and cut tree, then you are not stuck with it. You throw it out and again start. Okay, so that way it is very powerful. Okay, so we already have very good solvers for this. For example, CBC or Gurobi. And very good solvers for convex NLO, IP-opt, and filter SQP, for example. And as I said, this can come from AMPL if you don't want to implement your own differentiation code. Okay, so in fact, these all 5 steps can even be implemented within AMPL itself, because AMPL supports for loops, and you can get the solution, query the solution of MILO, add some cuts and repeat. Okay, so very, very simple in implementation and quite effective. Okay, and this doesn't have to advance in time, it automatically improves performance, because after every new release of an MILO solver, these will become faster and faster. With time, NLO solvers become faster and faster. So if you implement this algorithm today and test it 2 years later, it will automatically be faster. Okay, you don't have to worry too much. Okay, so that way it is very good and robust in that ways. Okay. The only drawbacks is that you have to repeatedly solve MILOs, and as their size increases, they get increasingly slower. Okay, so with time, the first MILO might be much simpler to solve, and it might take just a few seconds. But as you keep adding, it will go to minutes, then maybe even hours. Okay. So that is one disadvantage. The other disadvantage of these methods is that when your functions are not really convex, then they fail quite fast. Okay, so even if your feasible region looks convex, okay, and your functions are convex in in and around the feasible region, the methods may still fail, because sometimes you may add linearizations at points where those convexity conditions are not really satisfied. Okay, so then those linearizations, they are not valid when the function is not convex. Okay, and then so these methods tend to be very fragile for problems for which you can't really show that they are convex. Okay, so that is another drawback. Also, if you want to parallelize some of these parts, then this inherently is parallelizable. NLOs, depending on what solver you are using, can exploit parallelism, but you can solve multiple NLOs in parallel and get different linearization points to speed up things. Okay, so quite a lot of speed ups can be obtained there as well. Okay. So we hinted at the finiteness of this this method, and the basic underlying principle is this, which says that once you add these linearization inequalities at certain y star, then whatever the NLO solution you have obtained, that can't really be beaten by any other y star that satisfies those inequalities. Okay, so that means a finite number of y stars and finite number of NLOs have to be satisfied, solved. Okay, internally every NLO is an iterative procedure, and you may argue that convergence in the limit is hidden within the NLO, right? So if you look at what is happening inside the nonlinear solvers, they iteratively move from point to point, and many times they converge only in the limit. Okay, so that convergence in the limit is still there. Okay, it's just that it is hidden in this step. Okay, rather than being explicitly outside in the outer loop. Okay, so when these NLOs reach some tolerance, they stop, and the outer method ensures that that happens only finite number of times. Okay. All right. So I had only these small things to discuss in this very session, because we had slightly longish discussion in the previous one. So if there are some questions or things to discuss, we can talk about them.
So sir, any open solvers, do this where they internally use another solvers for MINLO and MINLO?
Actually, quite a bit, quite a few. So for example, Bonmin, which is available through CoinOR, it has 3 or 4 different algorithms for convex MINLOs, including this outer approximation. Okay, so internally it calls CBC for MILO, and IP-opt or filter. You can give various options and do it. Okay, so MILO. Okay, and it gets its derivatives from ample. Okay. The ECP method that we briefly talked about, where we add linearization at that particular point itself without solving an NLO, those implementations are also available. Okay, so there is something called short, which has the option to solve it using ECP. Okay. So even though we said that ECP might take a lot of iterations of MILO solver, in practice actually it is quite good many times. Okay. For small or medium sized problems, sometimes it is better not to call NL solver at all. Okay, so you just add a linearization at that particular point and quickly just call the MILO solver again and try to converge. So that also works. The other advantage of ECP type of methods is that you are not stuck to just the KKT point where you can add linearizations. You can do some bit of search around that point and add linearizations not just at, so suppose you are here, x star, y star. An ECP based method might add a linearization here which might chop it off but may not touch the nonlinear region. The outer approximation may find these tight inequalities. But if you are trying to do ECP, you can add some linearizations at x star, and you can people just try to explore some of the directions in and around this point and may add some additional cuts at other points, okay, which might actually be quite good. All right. Sometimes they do a line search, so they say that so what you can also try to do is suppose this is some one nonlinear constraint and you would like to be inside it, and suppose you are outside this point. So in the beginning of the algorithm, you can try to find one interior point of this constraint. Let's call it x naught, y naught. And this point is fixed. You try to find it right in the beginning by some interior point method or something. And then every time you are outside the region, you do a line search between these 2 points. So that means you find this direction D and take various step lengths and search up and down and try to come closer to this boundary and then add a linearization constraint here. Okay, and if you have multiple interior points, you can find more linearizations. Okay, so there is a lot of flexibility in these types of methods. In fact, tomorrow Sven is going to talk about LP and NLP methods which have even more flexibility, where you sort of integrate some of these steps even more closely inside a solver. So there's a lot of ways of enhancing this and improving the performance. one natural question that arises is that suppose I set a time limit on this MILO. Okay, so instead of solving this to optimality, suppose I am unable to solve it to optimality because it is taking too long. Okay, so suppose I stop it in between. All right. Then what happens? Okay, so I am following this algorithm by the textbook, but I observe that this is taking too long, so I break it. So I set a time limit of, let's say, 5 minutes. And I get some feasible solution. It may not be optimal solution of this MILO, but some other feasible solution, let's say X bar, Y bar. Then can we do something? Okay. You can add these cuts at any point actually. They don't have to be, coming out as the optimal solution of any MILO. Okay. These inequalities work for any point. Okay. There is nothing really sacrosanct about being optimal to MILP or anything. Okay. So if this Y hat, suppose this after 5 minutes it gave this as the best known solution. You can still add linearization cuts around this point. Okay, using the same principles, you can solve for a fixed Y bar and solve it. Okay. Hmm? If you solve MILO to optimality, then you will get a lower bound on MINLO. Okay. If you stop in between, the solver still gives a lower bound. It is a lower bound on a lower bound, so it is still a lower bound. Okay. Many times these solvers will give you a pool of solutions. That means multiple solutions, 5 or 10 solutions. You can try adding linearizations of all 10. Okay, so more linearizations. Just the trade-off is that in the next iteration this MILO might be slower, but the lower bound might be higher. Okay, so when you implement these in detail, there are a lot of trade-offs between various competing goals, and some care is required. Questions? All right, so in that case, we start with the next session by Sven in another 5 minutes or so.